Welcome to the unit of Hadoop Fundamentals on Hadoop Architecture. I will begin with a terminology review and then cover the major components of Hadoop. We will see what types of nodes can exist in a Hadoop cluster and talk about how Hadoop uses replication to lessen data loss. Finally, I will explain an important feature of Hadoop called rack awareness, or network topology awareness. Before we examine Hadoop's components and architecture, let's review some of the terms that are used in this discussion. A node is simply a computer. It is typically a non-enterprise, commodity-type hardware used for nodes that contain data. So in this example, we have node 1. Then we add nodes such as node 2, node 3, and so on. This would be called a rack. A rack is a collection of maybe 30 to 40 nodes that are physically stored close together and all are connected to the same network switch. Network bandwidth between any two nodes in a rack is greater than bandwidth between nodes on different racks. You will see later on how Hadoop takes advantage of this fact. A Hadoop cluster, or just a cluster from now on, is a collection of racks. Now, let's examine the pre-Hadoop 2.2 architecture. Hadoop has two major components. The distributed file system component, the main example of which is the Hadoop distributed file system, though other file systems such as IBM's GPFS FPO are also supported. And there is the MapReduce component, which is a framework for performing calculations on the data in the distributed file system. Pre-Hadoop 2.2 MapReduce is referred to as MapReduce version 1 and has its own built-in resource manager and scheduler. This unit covers the Hadoop file system, and MapReduce is covered separately. Let's now examine the Hadoop distributed file system, or HDFS. HDFS runs on top of the existing file system on each node in a Hadoop cluster. It is not POSIX compliant. It is designed to tolerate high component failure rates through replication of the data. Hadoop works best with very large data files. The larger the file, the less time Hadoop spends seeking for the next data location on disk. The more time Hadoop runs at the limit of the bandwidth of your disks, the faster the processing. Seeks are generally expensive operations that are useful when you only need to analyze a small subset of your dataset. Since Hadoop is designed to run over your entire dataset, it is best to minimize seeks by using large files. Hadoop is designed for streaming or sequential data access rather than random access. Sequential data access means fewer seeks, since Hadoop only seeks to the beginning of each block and begins reading sequentially from there. Hadoop uses blocks to store a file or parts of a file. This is shown in the figure. Let us now examine file blocks in more detail. A Hadoop block is a file on the underlying file system. Since the underlying file system stores files as blocks, one Hadoop block may consist of many blocks in the underlying file system. Blocks are large. They default to 64 megabytes each, and most systems run with block sizes of 128 megabytes or larger. Blocks have several advantages. Firstly, they are fixed in size. This makes it easy to calculate how many can fit on a disk. Secondly, by being made up of blocks that can be spread over multiple nodes, a file can be larger than any single disk in the cluster. HDFS blocks also do not waste space. If a file is not an even multiple of the block size, the block containing the remainder does not occupy the space of an entire block. As shown in the figure, a 450 megabyte file with a 128 megabyte block size consumes 4 blocks, but the fourth block does not consume a full 128 megabytes. Finally, blocks fit well with replication, which allows HDFS to be fault tolerant and available on commodity hardware. As shown in the figure, each block is replicated to multiple nodes. For example, block 1 is stored on node 1 and node 2. Block 2 is stored on node 1 and node 3, and block 3 is stored on node 2 and node 3. This allows for node failure without data loss. If node 1 crashes, node 2 still runs and has block 1's data. In this example, we are only replicating data across 2 nodes, but you can set replication to be across many more nodes by changing Hadoop's configuration or even setting the replication factor for each individual file. The second major component of Hadoop, described in detail in another lecture, is the MapReduce component. HDFS was based on a paper Google published about their Google file system. Hadoop's MapReduce is inspired by a paper Google published on the MapReduce technology. It is designed to process huge data sets for certain kinds of distributable problems using a large number of nodes. A MapReduce program consists of 2 types of transformations that can be applied to data any number of times: a map transformation and a reduce transformation. A MapReduce job is an executing MapReduce program that is divided into map tasks that run in parallel with each other and reduce tasks that run in parallel with each other. So let's examine the main types of nodes in pre-Hadoop 2.2. They are classified as HDFS or MapReduce version 1 nodes. For HDFS nodes, we have the name node and the data nodes. For MapReduce version 1 nodes, we have the job tracker and the task tracker nodes. Each of these is discussed in more detail later in this presentation. There are other HDFS nodes, such as the secondary name node, checkpoint node, backup node, that are not discussed in this course. This diagram shows some of the communication paths between the different types of nodes in the system. A client is shown as communicating with the job tracker. The client can also communicate with the name node and with any data node. There is only one name node in the cluster. While the data that makes up a file is stored in blocks at the data nodes, the metadata for the file is stored at the name node. The name node is also responsible for the file system namespace. To compensate for the fact that there is only one name node, one should configure the name node to write a copy of its state information to multiple locations, such as local disks or an NFS mounted disk. If there is one node in the cluster to spend money on the best enterprise hardware for maximum reliability, it is the name node. The name node should have as much RAM as possible because it keeps the entire file system metadata in memory. A typical HDFS cluster has many data nodes. Data nodes store the blocks of data, and the blocks from different files can be stored on the same data node. When a client requests a file, the client finds out from the name node which data nodes stored the blocks that make up that file, and the client directly reads the blocks from the individual data nodes. Each data node also reports to the name node periodically with a list of blocks it stores. Data nodes do not require expensive enterprise hardware or replication at the hardware layer. The data nodes are designed to run on commodity hardware, and replication is provided at the software layer. A job tracker node manages MapReduce version 1 jobs. There is only one of these on the cluster. It receives jobs submitted by clients. It schedules the map task and reduce tasks on appropriate task trackers, that is, where the data resides, in a rack-aware manner. And it monitors for any failing tasks that need to be rescheduled on a different task tracker. To achieve the parallelism for your map and reduce tasks, there are many task trackers in a Hadoop cluster. Each task tracker spawns Java virtual machines to run your map reduce task. It communicates with the job tracker and reads blocks from the data node. This lesson continues in the next video.